Section 8.3, the equations of rotational kinematics. We're at last to our kinematic equations. So remember, way back in chapter 2, the equations of kinematics for constant acceleration. We saw that we had 5 kinematic variables: displacement, x, acceleration, which is always constant, a, the final velocity at some given time, t, the initial velocity, v0, and the elapsed time, t. And that gave us these 4 equations that related those 5 variables to each other. We know that all the 4 equations have 4 out of 5 of the variables, and we're going to use the same analysis technique with these 4 equations and 5 variables. The only difference is that they're all going to become angular. So if we imagine these equations for a moment in the angular form, then we'd find that velocity would now be written as angular velocity. So the v's become omegas. The a's of acceleration become alphas for angular acceleration. The x's for displacement become thetas for angular displacement. The one variable that does stay the same is time is still t. So that's a little bit comforting. There's something familiar in the midst of it. So hopefully you can start to see the similarities. I really appreciate how the book has some tables that highlight the rotational motion, the quantity, and the linear motion, what variable is used, right? So for rotational motion, it's theta. For linear motion, it's an x. For velocity, it's omega in the rotational. It's v for the linear, but we still use the 0 for the initial and no subscript for the final. Acceleration is a versus alpha. T is the same. And then you have the 4 equations side by side. So if you're really more comfortable looking at the linear version of the equations that we saw in chapter 2, that's fair. You can just think in those terms and translate it back to the angular form. Now, just as we had before, we can have a reasoning strategy for rotational problems, a procedure, if you will, of steps to follow. So first off, make a drawing, because drawing is always our first step in solving problems, and it really helps to highlight things that you may not realize that you actually do know. You also want to decide which directions are to be called positive and negative. So the textbook uses counterclockwise as positive, but as I mentioned, it's a convention. So you can choose another direction as long as you're consistent throughout. I recommend sticking with counterclockwise as positive, clockwise as negative. It often simplifies things. Then you'll write down the values that are given for any of the 5 kinematic variables. This is where I recommend making a table again, just as we did in chapters 2 and 3. Verify that the information contains values for at least 3 of the 5 kinematic variables. Then you can select the appropriate equation that has those 3 variables as well as the one that you're looking for. When the motion is divided into segments, remember that the final angular velocity of one segment is the initial angular velocity for the next. This is the same bullet point we saw before, just with an angular velocity instead. And then keep in mind, there may be 2 possible answers to a kinematics problem. So that's something to think about, is we saw that there are some symmetry examples. Let's try this out with an example. So blending with a blender. You can always ask, will it blend? Well, here we're going to ask, how fast will it blend? So the blades are whirling with an angular velocity of 375 radians per second when the puree button is pushed in. When the blend button is pushed, the blades accelerate and reach a greater angular velocity after the blades have rotated through an angular displacement of 44 radians. You can figure out how many revolutions that is, but it's given to you in radians to make it simpler to solve. The angular acceleration has a constant value of 1740 radians per second squared. Find the final angular velocity of the blades. How fast are they moving? So a few notes here. Before we start recording our values, notice it tells us it's a constant value of angular acceleration. Since the angular acceleration is constant, we can use those kinematic equations that we had before. Also notice that the angular velocity, the angular displacement, and the angular acceleration are all positive. And this even matches in the picture. The axis of rotation is passing through the center of the blender, And notice if you look down from above, it is going in the counterclockwise direction, which is the positive direction. Now that we've made those observations, let's fill in our table, right? So what variables do we know here? Well, let's see, there's this angular velocity of plus 375 radians per second. Is that going to be our initial or our final? Well, it asks us to find the final angular velocity. So I'd say that's what we're looking for, and it's then giving us this 375 as the initial. So I'll plug that in as a positive 375 radians per second. Awesome. What else do we know here? Well, they hopefully write out the words like angular displacement. That really keys us in that they're talking about theta. They could have just mentioned they rotate over 0.44 radians. And then at that point, the units are your best clue as to what they're telling you. Radians, oh, that's my angular variable. So cool, angular displacement, 0.44.0 radians. Great. And then it gives us this 1740 radians per second squared, which we notice are the units of angular acceleration. So we can fill that in too. 1740 radians per second squared. So what variable do they not tell us anything about? Notice they make no mention of time. So in general, that means we're going to look for an equation that doesn't involve time, because it doesn't tell us the time and it doesn't ask for the time. We want an equation that has every other variable. That's going to be, if you remember, the velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Let's take a look. So remember this equation? Now it's written in angular form. So if we want to solve for the final angular one, we can take the square root, and it'll be the square root of omega squared plus 2 alpha theta. One thing to note whenever you're taking a square root is that on the outside, there is an implied plus or minus. That's where there are two possible solutions. We have to fill that in based on context. In this case, since we have a positive initial angular velocity and a positive angular acceleration, that tells me that the acceleration is acting in the same direction as the angular velocity, so we should have a larger angular velocity in that same direction. So we will choose the positive one here, and the number comes out to 542 radians per second, which is significantly faster than 375 radians per second. Wouldn't want to put my finger down there, right? Moving very fast. This introduces how we can use our rotational version of the kinematic equations, and we'll follow the same problem-solving strategy, just with variables that look a little strange. But you can say to someone, hey, it's Greek to me, and you'll actually understand what it's being referred to.